If you really want to get smarter, the best way is to learn the principles. Over the next 122 years, I'll break it all down for you. I'll walk you through the logic behind how all kinds of systems work. Today, let's take in an entire nuclear power plant in one go. From fuel assemblies, uranium fuel rods, nuclear fission, and neutron chain reactions, to control rods and the reactor pressure vessel, the primary cooling loop, pressurizer, steam generator, turbine, generator, condenser, and spent fuel pool, and then on to dry and wet storage plus the full set of passive safety systems. You'll get it once you've seen the whole picture. A nuclear power plant isn't some mysterious kind of power station, nor is it just a place where a nuclear reaction is shut inside and left to burn. What's truly clever about it is that it takes extremely violent nuclear fission and puts it inside a complete engineering system that can be controlled, isolated, cooled, and shut down. One that can even save itself after a blackout. A lot of people hear nuclear power and immediately think danger. But if you look only at the power generation chain, the underlying logic of a nuclear plant is actually pretty simple. First, it generates heat in the reactor, then it uses that heat to make steam, and finally, it lets the steam drive a turbine, which then drives a generator to produce electricity. What's truly complex is that this heat comes from nuclear fission. So the entire system has to be built around four things: keeping fission stable, controlling the reaction rate, continuously removing heat, and isolating radioactive risk layer by layer. Let's start with the reactor. The core of a nuclear power plant lies inside the reactor pressure vessel, where groups of fuel assemblies are placed. A fuel assembly is not one solid block of uranium, but rows of neatly arranged fuel rods. Inside each fuel rod are many tiny uranium fuel pellets, stacked one after another, and sealed inside a metal tube. These fuel pellets contain processed uranium-235. What makes uranium-235 special is that after its nucleus absorbs a neutron, it becomes unstable, and then splits apart. This process is called nuclear fission. During fission, a uranium nucleus splits into smaller elements and releases a huge amount of energy at the same time. That energy ultimately shows up as heat. More importantly, each fission event also releases new neutrons, and those neutrons go on to strike other uranium-235 nuclei, triggering more fission. That's how the reaction keeps propagating step by step. This is the chain reaction. But a nuclear plant can never allow the chain reaction to grow unchecked, because if there are too many neutrons, the reaction becomes too strong. Too few neutrons, and the reaction weakens. What a nuclear plant has to do is keep this invisible neutron dance within a stable range. The first control method is water. In this kind of pressurized water reactor, water not only carries heat away, it also has another crucial role: slowing neutrons down. Newly released neutrons move too fast and may not be easily absorbed by uranium-235. Water can slow those neutrons, making them more likely to trigger the next fission event. So inside the reactor, water is both the coolant and the neutron moderator. But boric acid is also added to the water. Boron is an element that is especially good at absorbing neutrons. By adjusting the concentration of boron in the water, you can affect how many neutrons in the reactor continue taking part in fission. The more neutrons are absorbed, the weaker the reaction becomes. The more neutrons remain, the stronger it gets. The second control method is control rods. Control rods are metal rods that can be inserted into the core, and they're made of materials that absorb neutrons. You can think of them as the reactor's neutron brake pads. The deeper the control rods are inserted, the more neutrons they absorb, and the weaker the fission reaction becomes. The higher the rods are withdrawn, the more neutrons keep hitting the fuel, and the stronger the reaction gets. There are different types too. Some control rods absorb neutrons especially strongly and are suited for rapidly suppressing the reaction. Others have slightly weaker absorption and are better for fine adjustment. There are also shutdown rods used specifically for emergency scrams. Once the system detects a serious problem, these shutdown rods quickly drop into the core and directly absorb large numbers of neutrons, suppressing the chain reaction. After controlling the reaction, the second problem is how to remove the heat. When the reactor is operating, the core continuously releases enormous heat. Primary loop cooling water enters from the middle section of the reactor, flows downward along the inside of the pressure vessel, then passes upward through the channels between the core's fuel assemblies. As the water passes around the fuel rods, it absorbs heat and its temperature rises rapidly. It then flows out through the hot leg piping on both sides of the reactor. The most critical point here is this: the primary loop water must keep circulating steadily. It passes directly through the core and is responsible for removing the heat released by nuclear fission. If that flow cannot be maintained, heat inside the core will keep building up, and the fuel and metal structures will enter a dangerous state. That's why the primary loop is equipped with powerful reactor coolant pumps that continuously send water back into the reactor. This system has to move an enormous volume of water every minute, for one reason only: to keep heat from lingering in the core. But that raises another question. The water temperature is already far above the normal boiling point of water. So why hasn't it turned directly into steam inside the reactor? The answer is the pressurizer. The pressurizer is connected to the primary loop, and its job is to maintain high pressure throughout the entire primary circuit. Under high pressure, water's boiling point rises. As long as the pressure is high enough, even if the water temperature is far above 100 degrees, it can remain liquid and won't boil inside the reactor. This is crucial for a pressurized water reactor, because what the core needs is liquid water continuously surrounding the fuel rods. Liquid water can remove heat steadily. If a large amount turns into steam bubbles, heat transfer becomes less effective, and the reaction state becomes harder to control. The way the pressurizer regulates pressure is very straightforward. When pressure is too low, heaters at the bottom heat part of the water into steam, and as the steam expands, the pressure rises. When pressure is too high, cooler water is sprayed in from the top, condensing part of the steam back into liquid, and the pressure drops. It works like the pressure regulator for the primary loop, keeping the high-temperature water in the reactor in the right state at all times. Next, the heat has to be sent from the reactor to generate electricity. But the primary loop water cannot be used directly to drive the turbine, because the primary loop water has been in contact with the reactor and must always remain sealed inside the nuclear island. It can't be directly mixed with the external power generation system. So nuclear plants use one especially critical piece of equipment, the steam generator. Its job is to let the hot water in the primary loop and the water in the secondary loop exchange heat through metal tubes. Simply put, the high-temperature water in the primary loop flows inside a bundle of U-shaped tubes, while ordinary feed water in the secondary loop flows outside the tubes. Heat passes through the tube walls, but the water on the two sides never mixes. This is extremely important. A nuclear power plant does not turn the reactor water directly into steam to drive the turbine. Instead, the water inside the reactor transfers heat through the tube walls to another clean water cycle. That way, the radioactive risk primary loop stays sealed inside, always separated from the external steam power system. The secondary loop water is heated to boiling inside the steam generator and turns into steam. As the steam rises, it also has to pass through multiple stages of moisture removal. That's because the turbine needs steam that is as dry as possible, not wet steam carrying water droplets. If water droplets are carried into the turbine by high-speed steam, it's like tiny stones hitting precision blades and can damage the equipment. So the upper part of the steam generator uses swirl vanes and baffles to fling out and trap the water droplets in the steam, allowing drier steam to keep rising before it is finally sent to the turbine. Now we move into the conventional island, the power generation section. The high-temperature steam first enters the high-pressure turbine. As the steam expands, it sweeps across row after row of blades, spinning the turbine at high speed. After the steam has done its work, both its temperature and pressure drop. It then goes through reheating and moisture separation, before entering the low-pressure turbine to squeeze out the rest of its energy. These turbines and the generator are connected to the same long shaft. When the turbine spins, it turns the generator as well. That's how electricity is produced. At this point, you'll notice that the power generation side of a nuclear plant looks a lot like many traditional thermal power systems. They all use heat to make steam, use steam to drive a turbine, and then use a generator to produce electricity. The difference is that, in a fossil fuel plant, the heat comes from burning coal or gas, while in a nuclear plant, the heat comes from uranium nuclei splitting. After the steam drives the turbine, it can't just be discharged. To improve efficiency, it has to be condensed back into water and recirculated. So the steam enters the condenser. Inside the condenser is another cooling water loop, and when the steam meets the low-temperature tube bundle, it releases heat, turns back into water, and collects at the bottom of the condenser. This condensate still can't go straight back to the steam generator. It has to go through purification, deaeration, preheating, and pressurization. First impurities are removed, then dissolved gases are taken out, then the water is pressurized by the feedwater pump, and finally it passes through the high-pressure heater to raise the water to the proper temperature before sending it back to the steam generator. The purpose of this is to prevent cold water from suddenly entering the steam generator and causing thermal shock, while also making the whole cycle more efficient. So a nuclear power plant actually has several separate water systems running at the same time. The primary loop water passes through the reactor and carries away the heat generated by nuclear fission, but it does not turn into steam and never leaves the nuclear island. The secondary loop water is heated into steam in the steam generator and goes on to drive the turbine and generate electricity. There is also the cooling water in the condenser, which is used to condense the spent steam back into water. Each of these water systems follows its own path. Heat is transferred between them, but the water itself must not mix freely. That is the core idea behind the multiple layers of isolation in a nuclear power plant. Now let's look at the protective structures outside. The reactor, pressurizer, coolant pumps, and steam generators are all enclosed within a robust containment vessel. Inside the containment are also the reactor pressure vessel, piping, and shielding structures. Outside that is an even thicker shield building and concrete structure. These shells are not just for appearance. Their purpose is to keep the reactor system confined within a controlled space. During normal operation, they provide shielding and protection. In abnormal conditions, they are responsible for keeping high-temperature steam, radioactive materials, and pressure within safe boundaries. But what really concerns people about nuclear power plants is this. What happens if something goes wrong? This brings us to the most important part of the AP1000, the passive safety system. So-called passive safety means it does not rely entirely on external power, nor does it rely entirely on operators taking immediate action. Instead, it uses gravity, natural circulation, spring-loaded valves, water tanks, and air convection to let the system automatically move toward cooling and shut down under severe conditions. If a serious anomaly is detected, multiple sensors will participate in the decision. Once the trigger conditions are met, the main power is cut off, and the control rods lose their holding force and drop into the core. The chain reaction is suppressed. At the same time, some valves are designed to fail open rather than fail closed. That way, even if power is lost, the cooling path can still open. Even though the reaction has been shut down, the core does not cool instantly. The fuel still has decay heat, and if that heat cannot be continuously removed, the temperature can still keep rising. So the system must keep cooling. In the AP1000 design, there is a passive residual heat removal path. Hot primary loop water can enter a heat exchanger and transfer its heat to water in a nearby tank. The cooled water then returns to the reactor by gravity and natural circulation. This process does not require large electric pumps to run continuously. It is sustained by temperature differences and gravity. If the reactor water level drops, there is also a makeup system. Above it are makeup tanks that can feed water in by gravity. And below there is a pressurized water tank that can rapidly inject water into the reactor when needed. In more serious situations, related water pools can also supply water to the core by gravity. There is only one goal: keep the fuel covered with water and keep carrying heat away. Looking further outward, the containment itself also helps with cooling. If high-temperature steam enters the containment, the temperature inside rises, and cool outside air is naturally drawn into the passages of the shield building. It flows along the outer wall of the containment and carries heat away. At the top, there is also a large water tank. Water can flow by gravity onto the outer surface of the containment, forming a film that absorbs heat and evaporates, further cooling the containment. This is the most ingenious part of passive safety. It doesn't wait for someone to rush in and save the day by pressing buttons. Instead, it puts the water up high in advance and designs the valves to open when power is lost, make the control rods drop when the power cuts out, and make the air channels rely on temperature differences to drive flow on their own. In other words, the very blackout the system fears most is instead used to trigger its safety actions. Next, let's look at refueling. Nuclear fuel isn't used until it's completely exhausted. After a reactor has been running for a while, the amount of fissile material in the fuel decreases while fission products build up, so the fuel assemblies need to be replaced. In general, after each operating cycle, only part of the core fuel is replaced, not all of it at once. Before refueling, the reactor is first shut down and cooled, and the pressure vessel head on top, and the control rod drive mechanisms are lifted away. The refueling cavity above the reactor is then filled with water. The water here isn't just for easier handling. It's also a radiation shield, so throughout the movement process, the fuel assemblies must stay deep enough underwater. Spent fuel is removed from the core by a dedicated refueling machine and sent through the transfer channel into the spent fuel pool. The pool is very deep, and the fuel assemblies are stored underwater. The water both shields radiation and continuously carries away the fuel's residual heat. Newly removed spent fuel is still extremely hot and can't be placed directly into its final storage container. It has to cool in the spent fuel pool for many years, and only after its heat drops to an appropriate level is it transferred to dry cask storage. Inside the dry storage cask is a metal inner canister, while the outer layer is made of thick concrete and metal shielding. After the fuel is loaded inside, the air is removed from the container and replaced with helium to improve heat transfer and reduce corrosion. Finally, the container is welded shut and moved to an outdoor storage site. At that point, you realize spent fuel is not some blob of green liquid, nor is it some mysterious substance flowing all over the place. The main high-level radioactive spent fuel is still those solid fuel assemblies. They're just no longer suitable for efficient continued fission. At the same time, they keep releasing heat and radiation, so they require long-term isolation, cooling, and management. Finally, if we connect the whole system together, nuclear fuel undergoes fission inside the fuel rods.
释放热量和中子。
Water slows down neutrons and also carries away heat, while borate water and control rods regulate the strength of the reaction. The primary loop stays liquid under high pressure and carries the core's heat to the steam generator. Through the tube walls, the steam generator transfers that heat to the secondary loop, which then produces steam. That steam drives the turbine and generator, and the condenser turns the steam back into water so the cycle can continue. The containment, makeup water tank, heat exchanger, gravity water tank, and natural ventilation channels are responsible for bringing the system back within safe limits when something abnormal happens. So the truly complex part of a nuclear power plant isn't that nuclear energy is somehow mysterious, but that it has to do 4 things at once. Keep fission going, keep the reaction under control, transfer heat steadily, and keep radioactive materials isolated at all times. That's why a nuclear power plant is different from an ordinary power plant. Every fuel rod, every control rod, every pipe, every valve, every water tank, and every layer of containment is not there in isolation. Together, they form a massive machine that slowly turns the energy released by atoms into electricity. The real question is, now that humanity can pack enough electricity for millions of households into a system this compact and this energy dense, should we really fear nuclear energy itself? Or should we better understand the design behind it that locks the risks within engineering boundaries?